Good morning, good afternoon, good evening. We are back, and we are better than ever. I'll tell you what love is. Love is mathematics, and in particular, the study of calculus, which we are continuing right now. We are going to try and finish up inflections and shape. I believe this will be the last installment. This is part 4. And what we're doing today, boys and girls, is we are going to use the graph of a function. This is the function. And we're going to use its properties and what we see to graph or sketch a graph of its first derivative and its second derivative. Okay? So first we're going to start with the first derivative. Let's talk about the first derivative, f prime. When f prime is less than 0, then I know the function is increasing. When f prime is greater than 0, hold the phone. When f prime is less than 0, when it's negative, I know that the function is decreasing. Hold the phone, Chuck, there. When f prime is positive, then I know the function is increasing. Very good. And when f prime, or the first derivative, is equal to 0, then I know that slope of curve must equal 0. Okay? So we know that. So let's start here. Where does the slope of this curve equal 0? And I think you can see about right here it appears to level off. This is a sketch, so we're kind of guessing, but I think we can agree that right there the function levels off and the curve has a slope of 0, which means the derivative must be equal to 0. So therefore, if the derivative is equal to 0, its graph will cross the x-axis there. So I'm going to assume it's right here on the y-axis that it's happening, and I'm going to put my point right there. Make sure you understand this. We are graphing the derivative, right? And so if the slope of the tangent to the curve equals 0, then the derivative equals 0. Therefore, the graph of the derivative will intersect the x-axis at that particular point. Okay? Where else does it appear that we go to a 0? Well, we come here and our function increases a bit, increases, and then we appear to level off somewhere in here. I'm going to say, I don't know, about, right in there somewhere. It's hard to tell, but it looks to me like it's about right here. So I'm going to go up here and I'm going to put another point right here where the first derivative is equal to 0. Okay, where the first derivative is equal to 0. So I know my graph is going to go through, the graph of my first derivative must pass through these 2 points. Now let's look at the behavior of the function, where it's increasing, where it's decreasing. Well, I think you would agree that from here down the function is decreasing until here. So decreasing here, that implies that our first derivative is negative. It's negative. And if the first derivative is negative, then its graph must be below the x-axis because its value is negative. Okay? Then we increase until we get to here and we're 0. So let's see. We are increasing here, which means f prime is greater than 0, or positive, which means it must be above the x-axis. So over here we're below the x-axis, then we're going to go above the x-axis. So let's sketch that part right now. This is the derivative, remember. Okay? So it's decreasing, so my derivative, the graph of my derivative, its value is negative, so it must be below the x-axis. Then it starts increasing slightly. Increasing, but it's going to go to 0, so I'm going to have to come back down, and I'm going to stop there just for a second, okay, till I figure out what's going on after this point here. Well, and it continues to increase, right? It continues to increase, so therefore the derivative, I won't write it again, must be positive. It must be greater than 0, so it must continue to be above the x-axis. And in fact, it's increasing greatly, a lot more than it was increasing here. It's increasing quicker, so the derivative is going to go quicker. And there we have a decent sketch of the first derivative. Now I'm going to go blue for the second derivative. Okay? The second derivative, let's just review real quick. When the second derivative is negative or less than 0, we know the original function f is going to be concave down when it's negative. When the second derivative is greater than 0, we know the original function is going to be concave up, greater than 0 or positive. And when the second derivative is equal to 0, we know that we have a point of inflection. Point of inflection. Okay? All right. So, remember, the second derivative is only the derivative of the first derivative. So the same rules apply here. The second derivative is going to be equal to 0 when the slope of the first derivative, or the graph of the first derivative, is 0. When does that happen? Well, it looks to me like it happens about here. I'm kind of close there. And then again right here, the slope is 0, right? Well, if that's the case, that means if the slope of the curve here is 0, the second derivative must have a value of 0. It must cross the x-axis. Yes? Okay, because the slope of the curve here is 0. The slope of the curve here is 0, and it happens to be on 0 as well. So we have a point in common between the first derivative and the second derivative. Also, the original function is concave up until about this point right here. And then it becomes concave down, right? And then it becomes concave up again. When it's concave down at about, it goes from concave down from about here to here, then our graph of the second derivative will be negative. It will be below the x-axis because its value is negative. So the second derivative is going to look something like this. Yes? Concave up to here, the second derivative is positive. Its value is, it's above the x-axis. Concave up here, above the x-axis. Concave down, below the x-axis, which means we have got some points of inflection. Points of inflection from concave, because we go from concave up to concave down, back to concave up. And let's take a quick look. The book did a nice sketch here. See how we did. And we did pretty good. We got our second derivative nicely. Nice little curve for our first derivative here. So we did okay. All right, one more example. And here we are given the first derivative, and we are asked to find a sketch of what possibly could be the original function. Now we can't be as accurate with the original function as we were before, but let's take a look here. Okay, let's find some x-intercepts. This is -6 here. This appears to be -1, and this appears to be 5. Okay, why am I doing that? Because now I can make a sign diagram of the first derivative, and let's see how that will help me. Okay, the first derivative. Okay, the first derivative, let's see, our critical points would be -6 because that's where the first derivative equals 0. It equals 0 again at -1, and it equals 0 again at 5. Okay? And to the left of -6, here, is this negative or is it positive? Well, it's negative because it's below the x-axis. So we have a negative, yes. Then we have a positive above the x-axis, below the x-axis, negative, and then above the x-axis, positive. And this, again, this is the graph of the first derivative. Okay? Well, what does that tell us about the original function? Well, if we just had this, we would say, oh, decreases and then increases. I have a local min at -6. And here, positive to negative. I have a local max at -1. And then negative to positive, I have a local min. Yes, decreasing to increasing. Yes, decreasing to increasing local min, increasing to decreasing local max. Okay, so I have a local minimum at -6, and this is where it gets a little bit tricky because we can't get a real good read, especially on a scale as varied as this. So I could, I could possibly put my local min up here or whatever. I'm going to choose to put my local min here. Okay, at -6, yes. And let's see, where else? I have a local max at -1, so maybe that's, up here, yes. And then a local min at 5, I don't know, it could be here, let's say. Okay, we'll put it, let's see, straight down here, a local min. So we have a local min, and a local max. Okay, and just real tiny, if this is a local min, then the shape must be like this, yes. If this is a local max, the shape must be like this. Oops, we'll make that a little bigger. And if this is a local min, the shape must be like this. So now we have a pretty darn good idea that the curve must look like this. The sign diagram tells us so. It must look something like this. And then it continues up here and continues up here. Okay? Well, what about points of inflection? Well, the points of inflection are going to occur when the slope of the graph of the first derivative is 0, and the graph of the first derivative, or the slope of the graph of the first derivative is 0 about here, which means this is where the second derivative is equal to 0. And the second derivative, when that's equal to 0, that's when the original function changes, in this case, from concave up to concave down, because it equals 0 here. Why does it equal 0? Because the slope of the tangent to the curve of the first derivative is equal to 0. Okay? Where does that happen again? Right? Where is the first derivative, or the slope of the first derivative, equal to 0 again? Right here. So if we go up, looks like we have another point of inflection about right there, because we go from concave down to concave up. Now, these mins and local mins and maxes could be just about anywhere, and we can talk more about that in class. But let's see how we did. Looks pretty similar to the book, except their point of inflection is a little bit off, right? And the point, the point of inflection occurs on the curve, not on the x-axis, on the curve where straight down from where the first derivative is equal to 0, or in this case, straight up from where the slope of the first derivative is equal to 0. I misspoke there. Straight up from where the slope of the curve of the derivative is equal to 0, or straight down, I'm sorry, onto the curve of the function. Okay, we'll straighten up any misconceptions in class. It is kind of tough, but you all can do it, I know. I am out!